This is a function, and this point, let's say it's p, x, f of x, and this point is q, x plus a little bit, f of x plus a little bit. So the difference quotient is nothing else but the slope of the secant line. So that's a difference quotient, which by definition is f of x plus h minus f of x divided by h. X plus h minus x is h. So this is our difference quotient, and we should never forget it. Okay. Then we are asked to simplify the difference quotient for this particular function. So all I have to do is plug in the function here and plug in the function here, and then simplify this as much as possible. So I will have 2x plus 2h minus 1 over x plus h plus 2 minus the function 2x minus 1 over x plus 2 divided by h. Now, we should all have this right. Is this okay? Are we okay with?
Why is q x plus h if it says a there? Why is q x?
I didn't get to that part yet.
Okay.
I'm just doing the first. Find and simplify the difference quotient. This graph only reminds you what the difference quotient is.
Okay.
Has nothing to do with the function itself. So this is an easy way of remembering what the difference quotient is. You imagine a function, you imagine p of fx comma f of x, and then you imagine q, a point next to it. And that's the definition of the difference quotient. So one more time, this has nothing to do with the function. This only constructs the difference quotient. Everything else so far is okay so far? Are we okay? Yes? Okay, so then I have to find the least common denominator, which must be the product of the two. So it's x plus 2 and x plus h plus 2. Now, I am meeting with my pre-calculus class, which is right before your class. I'm meeting in this room roughly about 4:30. If you are on campus, if you think you need help, please come. Okay? So I have about half an hour, or even if you want to come earlier, let me know, and I'll help you with anything you need. Just that we cannot fall behind, please. Okay, so I need an x plus 2 here, and I need an x plus h plus 2. Before I even think about this and how to simplify it, I know exactly what I'm getting at. What has to happen eventually? I don't even know. I don't have the calculations yet. But what has to happen eventually, for sure?
Cancel out the h's.
Not all of them.
Okay.
This particular h eventually has to go away. If it doesn't, something is wrong. That's one thing. What is the second thing that must happen at the top? All terms without h must cancel out. Not all terms. You can't have 0 at the top, right? All terms without h must go away. Is that okay? So two things you have to remember. Every time you find the difference quotient, all terms at the top that does not have h must go away, and this h eventually has to go away. So this is what I'm thinking of. I have no idea where I'm getting at, but I know that that must be the case. Okay, so now I start distributing x to these three terms, 2x squared plus 2xh. We did a problem like this in class. So let me allow me one more time to remind you how to study for this class. You must redo the problems we do in class first. Then read the examples that are solved in the book, and then solve as many odd number problems as you can. Okay? It takes time to build this confidence and skill. Okay, so I'm back. N minus x, and now I distribute 2 to these three terms. So I have 4x plus 4h minus 2. Now I distribute 2x to these three terms, but I have to multiply by -1. negative 2x squared, negative 2xh minus 4x. And then I distribute negative 1 with minus in front, so I'm distributing 1. So plus x plus h plus 2. If terms without h don't go away, I made a mistake somewhere. So let's check. The 2x squared with negative 2x squared, and some other terms, but definitely those without h have to go away. So this is all it's left, this and this. So I have a 4h and an h. So then I have 5h divided by x plus 2, x plus h plus 2. This is h over 1, so I have to multiply by 1 over h. And everything that I predicted happened. The terms without h went away eventually. In this case, some other terms with h. That's fine. But I cannot have 0, of course. And the h from the denominator got simplified. So then this is the difference quotient. So maybe working also in WebAssign will really help you. So if you consider doing that, the course is there. You have the class key. You can log in. Okay, so my first question is answered. Find and simplify the difference quotient for this function. I did. I found it and I fully simplified it. Then find the slope of the tangent line to the graph of the function at this point. So I have the point P, negative 1, negative 3. And I also need to make h approaching what to find the slope of the tangent line at P? So these two have to happen. So first, the point P, negative 1 comma negative 3 means x equals negative 1. That's what it means. So then from here I have that the difference quotient will approach what when h approaches 0. So when h approaches 0, this term goes away. I have x plus 2 times x plus 2. So this will be 5 divided by x plus 2 squared. So when h approaches 0, the difference quotient approaches 5 over x plus 2. All I have to do in this expression is make x equals negative 1. So then I will say the slope at P is how much? Oh, the tangent line, of course. The slope of the tangent line at P is? Thank you. Now, I specifically did not want to put the y-coordinate here. Can anyone give us the y-coordinate? I'm going to go to the next page. Can anyone give us the y-coordinate of that point? I'm sorry?
It's 5 over a plus...
No. The y-coordinate first. Yes, of course. I cannot guess there, right? Of course. So it's q, a comma, 2a minus 1 divided by a plus 2. Of course, there is no discussion there. If I'm given a function and I'm told x is a, then I know the y-coordinate of that point. Perfect. So now I want to determine for this point, which is a comma 2a minus 1 over a plus 2. I already have the difference quotient, which is this, and I want to determine the slope of the tangent line at Q. What will be the slope of the tangent line at Q?
5 over a plus 2.
Absolutely. Once I have the difference quotient, then I fully simplified it. I can say, and I also make h approaches 0. Then I have the slope of the tangent line. This is the slope of the tangent line to the graph of f at any point where the function is defined, and later on we'll understand differentiable. So at this point, I determine the slope of the tangent at this using the definition of the slope at any point, the function that gives us the slope at any point. I can determine when x is negative 1, I can determine exactly the slope of the tangent line at P, which is 5. I can also determine exactly the slope of the tangent line at Q with x being a, as being 5 divided by a plus 2 squared. Any questions on this? Yes?
Why are we doing it as h approaches 0?
Okay. So the difference quotient is nothing else but the slope of this line. So when I want to determine the slope of the tangent line at P, this point gets closer and closer, closer and closer to P, which means this number gets closer and closer to 0. Very good. Other questions? Okay, so let's go back to this handout. I do not keep all quiz grades. I keep few of the best grades you have. The quizzes should just tell you this. If I cannot do it with the open notes, I have not studied enough. I have not watched the videos, once from the last semester and once from now, so I can see more examples. I have not read the book. I have not worked on the examples we did in class. I have not looked at the homework. I have not looked in the book. I am not prepared. That's all I want you to say, if that's the case. If that's the case, and then put yourself in gear. That's all I care about. Okay, so we did not finish this, and I wanted to talk about it and then continue with 2.3 and hopefully 2.4. So we already looked at some functions in which the limit as x approaches a from that particular function was either negative infinity or positive infinity. It can be a limit from either side, or it can be a limit from one side. Infinity or negative infinity. And I wrote here several situations. What can happen? From either side to be infinity, from either side to be negative infinity, from the right hand side to be infinity, from the left hand side to be infinity, from the right hand side negative infinity, and from the left hand side negative infinity. In all these situations, x equals a is a vertical asymptote. In other words, and this is an example, as you see, as x approaches 1 from the left-hand side, function values get closer and closer to infinity. As x approaches 1 from the right-hand side, the function values get closer and closer to negative infinity. It happens then, what would you say? As x approaches 1 from either side, what will you say? Say it again? Yes. Well, what about the limit? As x approaches 1 from either side, what would you say the limit is? It's d and e. We don't say undefined. You're right. I mean, I know what you mean, but we have to say d and e. Yes, it does not exist. Very good. So that's why x equals 1 for this function is a vertical asymptote. If one of the above happens. So when does a function have a vertical asymptote? If at least one of the limits as x approaches a from the left, from the right, or either side of f of x is positive or negative infinity, then f of x, and then x equals a is a
Vertical.
thank you. Vertical asymptote of f of x. Any questions on this? Okay. I gave a few examples here. Sorry that it's not very clear now because I wrote on the other side. I forgot that I have the handout back to back. So here I plotted an exponential function. So 2 to the x, which is this function. Careful, it does not touch the x-axis between -6 and -3. No, that's not the case. So be very careful. It goes on forever. We say eventually it may touch the x-axis, but not here. Okay, if for this function we're asked to determine limit as x approaches negative infinity of 2 to the x, what will you say looking at the graph?
Can you repeat that?
Yes. So limit of 2 to the x as x approaches negative infinity. I just don't want to wait till later on. I want to analyze these graphs as soon as possible. Can anyone, by looking at the graph, tell us what the answer is?
You?
Of course. Which means y equals 0 is a horizontal asymptote. Indeed. Very good. Okay, let's look at the same graph. I'm going to ask limit as x approaches infinity from 2 to the x. Very important to remember these graphs. This is an exponential function with a base greater than 1. So what will you say about the limit as x approaches infinity? Can anyone tell us?
Y approaches infinity.
Of course, the limit is infinity. Indeed. Look at the graph. It goes up forever. So the limit as x approaches infinity, the function approaches infinity, so the limit is infinity. As x approaches negative infinity, the function values get closer and closer to 0, which makes y equals 0 a horizontal asymptote. Do we see this? Yes? Do we all see it? Okay, let's look at the natural log. So now we want to look at the graph of natural log x as x approaches 0 from the right. And then I'm going to ask a limit as x approaches 0 from the left. And one more, I'm going to ask the limit of natural log x as x approaches infinity. Okay, so let's look at the graph of natural log. We have to remember this. The graph is this. It crosses at 1. And I would like you to tell me the limit as x approaches 0 from the right. What would you say?
2, 0.
So the graph is like this.
So negative.
Negative infinity. As x approaches 0 from the right, the graph approaches negative infinity. Do we all agree with this? Do we all see it? Okay, perfect. Now I want the limit as x approaches 0 from the left of natural log. What will you say? Let's look at the graph.
0.
Let's look at the graph.
0 next to this.
Of course, the function does not exist on that side. Absolutely. That was a little tricky question. Very good. Now, limit of natural log as x approaches infinity. Oh, and by the way, when I have this situation, what do I conclude about x equals 0? Look at the graph. As x approaches 0 from the right, function values go to negative infinity. What can we say about x equals 0? Look at the graph again.
Doesn't exist.
X equals 0 is
Vertical asymptote.
vertical asymptote. Good. So now we want the limit of natural log as x approaches infinity. So I'm kind of asking you to file all these handouts, because we are going to go back, or you will have to go back to them when you study for the test. So please do not throw these away. I'm going to post them also in Canvas. Okay, so limit of natural log as x approaches infinity. What will you say? Look at the graph. So as x approaches infinity, function values approach 3? Infinity. Very good. Thank you. That's infinity. Very good. So let's look at the next graph, which is tangent x. So can you give me some limits about tangent x? What could I ask you? Just dictate, and I'm going to write it. Limit of what? Of tangent x. So I could ask you what? As x as x approaches negative infinity? I could not ask you that.
-2 or
Let's look at the graph. Okay, one more time. Here's the graph of tangent. What kind of limits can I ask you about this graph? Yes, pi over 2, exactly, of tangent x. This is pi over 2. This is negative pi over 2. These are the asymptotes of tangent. So what could I ask you, for example? As x approaches pi over 2 from the, very good, from the left, what is the limit? As x approaches pi over 2 from the left, where do the function values go? Okay. And then limit. As x approaches, what else can I ask you? Very good. Negative pi over 2 from the, very good. And according to the graph, the limit will be, no cell phones, please. Very good. What do we conclude then? This will give us a conclusion. This will give us a conclusion. Very good. And from this one? Yes? Very good. Perfect. Okay, couple more. Okay, so this is the arctangent. And in Maple, I had to name these differently so I'm able to show them to you. Okay, so this is the graph of arctangent, the inverse function of tangent. Okay, so what limits can I ask you here? Limit arctangent or tangent inverse. So the same thing is the same notation, tangent inverse. So what can I ask you? Limit as x. So as x approaches infinity, what will this be? So as x approaches infinity, yes, roughly it's pi over 2 to be exact. Yes, indeed. So then what will I conclude about y equals pi over 2? Horizontal asymptote. And I can also ask you a limit as x approaches negative infinity from arctangent x. What will you say? Yes, negative pi over 2. So then y equals negative pi over 2. By the way, horizontal asymptote at infinity. And this is the horizontal asymptote at only negative infinity. So please remember these graphs, okay? Tangent, arctangent, exponential, logarithmic. Okay. So these are three functions called hyperbolic functions. Hyperbolic functions. So this is one of them. I only graphed hyperbolic cosine x. It does look like a quadratic function with a positive slope, with a positive leading coefficient, with a positive leading coefficient. But it's really not. So let's just define these three functions. Let me show you. I know they are at the end of chapter 3, but I just wanted to show you these three functions. So when we get to that section, I just want to show you the use of these, the applications of hyperbolic functions. So this is a very typical application of the hyperbolic cosine. Between two poles, when they stretch a cable, it could be phone or something else, they determine the distance between or the length, I should say, forgive me, the length of the cable using a hyperbolic cosine function. And the other application are the ocean waves. So the hyperbolic functions are very good for that situation, as you see, something with a tangent, hyperbolic tangent function. So we know now all functions that are ahead of us. So now let's write the definition for hyperbolic sine, hyperbolic cosine, and hyperbolic tangent. Hyperbolic tangent will be very clear, will be the hyperbolic sine divided by hyperbolic cosine. There is no question there. But what about sine? So e to the x minus e to negative x divided by 2, that's the definition of hyperbolic sine. And the definition of hyperbolic cosine is identical but plus at the top, in between. So this definition is e to the x plus e to negative x divided by 2. So now we pretty much have all functions that we are going to encounter throughout this semester. Trig functions, inverse trig functions, polynomial functions, rational functions, log and exponential, and hyperbolic. That's pretty much it. Okay? And I would like to consider this done, and I will kindly ask you to add this to your homework, and we can talk about it next time, because I would like to move forward. Okay, I gave you a handout last time on 2.3. I'm just looking for one for myself. And we're finally ready to talk about limit laws. How do I calculate limits? There are so many different situations. I do have a concise summary, I would say, or a summary of all possible types of limits that we will look at this semester. And I will copy and have it for you on Wednesday. So let's start at the top. I'm going to try not to write on this so I can use it. The backside. I can use the backside. So what do you think the limit as x approaches a of x is? What did I say the first thing we have to do? Even if we just do it in our head, what is the first thing I need to do when I'm asked to calculate or evaluate a limit? No. Plug in what I have, what is given. X approaches blah. I have to plug in blah. I cannot just make up a number. Exactly, that's it. Done. Okay, now let's look at the rest of the limit laws. So this is 2.3. This says we are given, this is given in our theorem here. If the limit of f of x as x approaches a from either side is L, what does that mean? It means that the limit exists. It means that the limit from the left and the limit from the right are the same number. Does it mean that the function is defined at a? No. It does not mean that the function is defined at a. It only says that the limit from either side is 7, which definitely means the limit from the left and the limit from the right are both 7. But it does not mean that the function must be defined at that point. We don't know. Okay. Second part of the theorem. Limit of g of x, it's a different function. As x approaches a from either side is m. What does that mean? It means that the limit from the left and limit from the right for function g, both exist, are the same number. What number? M. Does it mean that that function g is defined at a? No, it does not. That's not required. What is required is that both sides of the function values approach the same number. Why it's not required for the function to be defined at that point? Because I'm not allowed to plug in a. So the limit may still exist, but I can never make x equals a. And you can say now, wait a minute. You just made x equals a. You just told me that x cannot be a, and you just plugged it in. True. Why? Because although x is not a, in the function y equals x, this is the function, this is this function, y equals x, as x approaches a from either side, function values approach a from either side. That's the reason why the answer happens to be a. That's why. Although I literally plugged it in because I knew the answer. I'm allowed to plug it in because that's how we determine the limits of polynomial functions. But then I'll say x is not a. Why does that happen? It's simply because as x approaches a from either side, function values approach a, in this case, from either side for polynomial functions. And other functions as well, but for now, this is a polynomial function. Y equals x is this function. Okay, so assuming that these two functions have limits as x approaches a from either side, and one limit is L and the other one is M, the limit of the sum or the limit of the difference of those two functions as x approaches a, that's the first limit law, is, so limit as x approaches a from either side from f of x plus g of x equals the limit of f of x as x approaches a plus the limit of g of x as x approaches a. In short, what does this equal to? Exactly. L plus M. Very good. Now, what if I have the difference? So how will you explain this to someone who does not know calculus? You will say, limit of the sum is the what am I pointing at? Is the what? Exactly. Thank you, Charlie. Exactly. What about the difference, the limit of a difference? What will you explain it? As the difference of the limits. And the same here. But what is the mandatory condition here? Say it again. No. Yes, John. Those have to be numbers. In other words, those two limits have to exist, in other words. If they don't exist, I cannot use this. Let me give you an example. So, at any point in time when I apply a limit law, my first question in my mind is, hey, can I apply it? Do those two limits exist? If they don't exist, I cannot apply it. So here's an example. So limit 1 over x minus x as x approaches 0. You cannot write limit of 1 over x minus limit of x as x approaches 0. Can anyone tell us why we cannot write that? Nope.
Because the limit x over 0 of 1 over x
does not exist. The graph of 1 over x, by the way, is this. So as x approaches 0 from the left, the limit is negative infinity. As x approaches 0 from the right, the limit is positive infinity. So therefore, this is D and E. So the limit law, this limit law, is not applicable in this case. Why? Because this one doesn't exist. This one is 0, but this one does not exist. Okay, next limit law, what will you say? Yes, so I have to write the limit as x approaches a, and please put it in. Limit of x approaches a from f of x times g of x is the limit of f of x times the limit of g of x as x approaches 0 from both, of course, and this is indeed L times M. Okay, what do you think about the part C? So the limit x approaches a from either side from f of x divided by g of x. What will you say?
X through J of X, 11x, then X equals A, G of X, but G of X can't be 0.
So it's L divided by M, and M cannot be 0. Very good. Perfect. That's why the if. That's why the if in this one. Okay.
If X what?
The denominator cannot be 0 in a fraction. Very good. Next one. Limit of f of x raised to the nth power. So limit of f of x raised to the nth power as x, of course, approaches a. This is a very important concept. So here's what I'm going to do. And this is used later in a lot of situations. See, this is the limit operator. This is a function, right? Power.
Is that A? What does that say? What's M?
It doesn't matter. You want to use M or N? I use any number. It's not important. So, of course, we don't know that yet. We don't know that yet, but we will talk about it in the next section. The function must be continuous. I'll explain that when we get to it. I am allowed to swap the two operators. So I will change the place of the limit and the power. So now the limit is outside, the power is inside. This is the same with this. Or M, since I changed it to M, allow me to put M. So this is limit as x approaches a from f of x. So under certain conditions, we are allowed, because they are the same, and the condition is the function to be continuous. So we are allowed to swap these two operators. So the limit of a function to the mth power is the same with the limit of the function, everything raised to the mth power. So obviously, since I know that this is L, the answer will be this. So keep in mind swapping operators, because I'm going to get to that theorem later on in the semester. Okay? So I'm allowed, under certain conditions, I'm allowed to swap operators. In other words, this goes outside and this operator goes inside under conditions of continuity. Okay, what will you say about limit as x approaches a from the nth root of f of x? Of course, n is a positive integer. The same swapping of the operators. What will you tell me to do? It's the same idea from the previous. It's the nth root of limit as x approaches a from f of x. And then you'll give me the simplified form. I'm allowed to do this under certain continuity conditions. Otherwise, I won't. It will not be the same. So then, this will definitely be the nth root of. Very good. Okay. And we have the limit of a constant. I know you can even say it sounds silly. And I would have to agree. But I still have to write it. It's a limit law. What will you say? What is the limit of a constant when x approaches? Will a constant ever change? If x goes to positive 5 or negative infinity or negative 3. So what is the answer? Of course. no discussion there. And then the last one here, limit as x approaches a from either side, from k multiplied by f of x. It's a factor, it's a number in front of a function, and I'm allowed to take it outside. We're going to do that a lot with a lot of things, including integrals. So this is k, limit of f of x as x approaches a. And ultimately, this becomes, that's it. Okay, and I want us to look at the note, and then we'll practice with as many problems as we can. Okay, if f of x, since we already have talked about this, let's see what you come up with. If f of x is a polynomial, even a rational function, and a is in the domain of the function, then the limit of f of x as x approaches a from either side will be equal to, what do you think? And it's obviously very similar to number 1. What will that equal to? A wild guess. What do you think?
0.
Exactly. That's what we did. That's what we did here. We just plugged it in. So that's what I was saying a minute ago. This is allowed only in certain conditions. And the conditions are polynomial function or rational function, but found in the domain. For the rational. Very good. For a polynomial, the polynomial is defined everywhere, so every time I find a limit of a polynomial, I just plug it in and I'm done. If it's a rational function, if f of x is a rational function, then I have to be careful. Because if there is a vertical asymptote, I cannot just plug it in, because I'm not going to get anything. Okay, so now I would like you to choose. I don't think we have time for all of them, but I'll let you choose whatever you want, and we'll work on those problems. And then I would like to present the squeezing theorem. Which one? I. This one. Okay, perfect. Perfect choice. So I have limit as x approaches 2 from the square root of x plus 2 minus the square root of 2x, x squared minus 2x. So from now on, every time we encounter a different type, we're going to talk about it. Okay? So I look at this limit and I look at the function. Let's identify the type of function. Yes, it has a ratio. Yes, it has radicals at the top. That's what I see right away when I look at the function, right? I see radicals at the top, I see a polynomial at the bottom, and a ratio. Okay, I'm asked to find this limit. The first thing that I have to perform, even if it's just in my head, is what?
Get rid of it.
What doing?
Say it again?
You want to put the doing?
Exactly. You have to remember this. This is the first step. You write it down. If this is something that you need to write down, every time I'm asked to find the limit of anything, I must plug in whatever number is there, or infinity, whatever it is. In this case, 2. So when I plug in 2, what do I get as the top? At the top.
0.
Thank you. When I plug in 2, what do I get at the bottom?
0.
Okay, now I'm asking myself this. That's my next step. Is there hope?
Yes.
There is hope. In 0 over 0, there is always hope. There is no guarantee, but there is hope. Perfect. Then I look at the function again. There is hope. That's my step 2. My step 3 is I look at the function again, and I say to myself, what can I do to this? Because eventually I need to simplify it. And what is the only thing I can do to this expression? Any algebraic manipulation that we've done so far, many times before this class, for a function like this. What are we trying to do? Get rid of the radicals, so sort of. I cannot really, but you're on the right track. How is it called? How is the process called?
Fractional as a numerator.
Excellent. This is a little bit contradicting to what we know from before. Always rationalize the denominator is true, but in this case, the problem is that the numerator. Excellent. Thank you, Rihanna. What? How do I do that? Say it again. Nope. Just get in.
Square.
It's like saying, okay, I have $10 in my pocket. Let me square it. It's not going to happen.
Multiply the top and the bottom by the square root of the.
The conjugate, very good, excellent. Which is basically 1. This is 1. I did not change the problem. Squaring is not going to work, right? But multiplying and dividing by 1 in this format, exactly this format, it's going to work. Perfect. So now I have limit as x approaches 2. The denominator is x squared minus 2x in parentheses, and in parentheses again x plus 2 plus the square root of 2x. Excellent. Wonderful. Thank you. And can anyone dictate the top?
X plus 2 minus 2x.
Very good. Excellent. This is on our contract. A plus B times A minus B is on our first contract that we made, the first agreement we made on the first day of classes. A minus B times A plus B is A squared minus B squared. Good. Excellent. Now I will combine my terms, simplify as much as I can, and remember the 2 key words. Factor, simplify, factor, simplify, factor, simplify. What can I do at the top? So what do I get at the top? Well, I know you know what is x plus 2 minus 2x. I have no doubt. What is it?
2 minus x.
2 minus x, but I want to put it in descending order, and I'm going to factor out a negative 1. Very good. Indeed. 2 minus x, but it's not in descending order, and it has a negative leading coefficient. So it is indeed 2 minus x. Good. Now I look at the denominator. There is nothing I can do here, but what will I do here? Factor, simplify, factor, simplify, factor, simplify. Excellent. Since we plugged in, I want to stop here for a moment and just have a little discussion. I plugged in x equals 2, and I got 0. What does that mean? When in an expression I plug in x equals 2 or x equals 5 or x equals negative 3 or whatever number you want, and I get 0, what does that mean? What does that say about the expression? If in an algebraic expression I plug in a number and I get 0, what does that say about the algebraic expression? Let me give you an example. Say it again. So let's say I have x squared minus 3x plus 2. Let's say I plug in x equals negative 1. X equals 1. Let's say I plug in x equals 1. What do I get in this expression? I'm going to call it p of x, a polynomial of x squared minus 3x plus 2. And I plug in 1. What do I get? P of 1. Perfect. What does that mean? What is the implication? What do I know now for sure about this polynomial? No question, no doubt. Exactly. That this polynomial has a factor of Thank you. P of x has a factor of x minus 1. This is the meaning. Extremely important. This is the factor theorem, the remainder theorem. So when I plug in 2, and no problem, when I plugged in 2 and I got 0, I know exactly that a specific factor must go away. No questions, no doubts. Which factor must go away? Factor, not a number. I'm talking about factors. X minus 2. So when I plug in 2 and I get 0 over 0, it is guaranteed that the top has a factor of x minus 2 and the bottom has a factor of x minus 2. Guaranteed. Okay. It's there. I already see it. Of course it's there. It's a must. When I plug in one more time, when I plug in a polynomial or an expression, a number like x equals 1, and p of 1 in this case is 0, then I know that x minus 1 is a factor of p of x. If I plug in -3 and I get 0, which factor does that polynomial have or expression have if I plug in -3? What factor must come out? X plus 3. Very good. So I knew from the beginning. You picked the problem. I didn't even look at it carefully. So x approaches 2. Once I plug in 2 and I get 0 over 0, I knew from that moment that from the top, an x minus 2 has to go away, and from the bottom, an x minus 2 has to go away. There is no guarantee that the limit exists, but I know for sure that one factor of x minus 2 from the top and one factor of x minus 2 from the bottom must go away, and that's what it is. And now finally, can anyone give us the final answer? Notice that I always write this 1. The reason is, some students say when some factor goes away, they think that there is 0 left at the top, and I don't want that. I want to avoid that possibility. So please tell me what to write. Over
X times X.
I cannot just, when I write the limit when this goes away, I can no longer have x. I can no longer have the limit. I have what? -1 over? As x approaches 2, where does this go? Okay, let's go back to our notes. As x approaches 2 of x, what is the answer? 2. Okay, very good. So this is 2. And where does this go as x approaches 2? Where does this go?
2.
How do we guess 2? Right. 2 plus 2 is 4. The square root of 4 is 2. The square root of 4 is 2. 2 plus 2 is 4. So what is the limit then? -1 over 8.
So all the x's go away?
X approaches 2. Yes.
So we
Hold on just one second. Nestor, is this okay?
Yeah.
Yes.
So we are allowed, so to speak, to use that once we have completely factored and simplified down. We'll be happy to
I no longer have 0 over 0.
Okay.
Very good question. I'm in the situation of the theorem. If f of x is a polynomial, in this case it's a rational function, and a is in the domain of the function, then limit of the rational function as x approaches 2 is f of 2. Good. I know we need more examples. I know that that's not enough. So let's look at another. Any questions? We're asked to find the limit, right? We're asked to find the limit of a function as x approaches a number. Would you like to choose another?
Okay.
Very good. So we're given limit of f of x as x approaches 2, and the f of x is given to us. X plus 2 greater than or equal to 2, negative x plus 5 for less than 2. Perfect. Perfect example. Good. So then, any suggestions?